Okay, in section 8.5, we're going to talk about the ionic portion of bonding. And we look at this ionic cube, and we remember that this is like a one-to-one, we could say NaCl. Remember that NaCl is not its own little molecule, but it exists in a repeating grid of NaCl ions. It is a lattice. Okay, and how that lattice forms and how we get the energy of that, since I can't just look at a single molecule, is the focus of today. What's the energy value there? The lattice energy, when we get to balanced equations, we have to have a couple of conditions met before we can make this guy over here. All the molecules need to be atoms. Okay, so we need to break any bonds that might be holding them together before they can make the lattice. They need to be ionic, so have a charge. And they need to be gases. They're going to spread out and just kind of deposit on one another. That's how we're going to treat this. They have to have individual atoms that are charged and in the gaseous state, and then they can come together to make a lattice. So write the chemical equation showing the lattice energy for these substances. So lithium is going to be a positive 1 ion, and it has to be a gas. And then that will combine with a fluorine negative 1 ion that is a gas. And that'll make an LiF solid. Okay, so this is the lattice energy equation. We will get an enthalpy for this. This would be the lattice energy. Okay, the energy of making the lattice from individual atoms that are ionic in the gaseous state. Magnesium is +2, gas. Oxygen is -2. We'll put that in the gaseous state. So gas ions make the solid, MgO. Okay, this is the lattice energy equation. So we've seen formation equations, combustion equations, dissociation, neutralization. This is the lattice energy. You need to make sure you have separate ions in the gaseous state. Calcium is +2, gas, +2 Cl minuses. Those are two individual atoms. That's fine. 2 Cl gases make CaCl2 solid. And then the last one, potassium chloride, potassium plus gas plus Cl minus gas makes KCl. Okay, the rest of our time we're going to look at the energy requirements required to do that. So here is a formation equation. All right. So the energy of formation, how do I make this solid from elements in their natural state, which could be solid, liquid, gas, or diatomic, and none of them are ionic. We have to go through this process in order to get to these separate ion gases where we can make the lattice. So there's a process to go through here before we can make that solid. This is just my formation equation. So how do we get the formation equation? Okay, what's the heat of formation of this guy? Well, we need to account for all of these things. All right, so let's take all of these in turn. The first one we're going to do is lithium. Okay, lithium is going to start out as, it's kind of like Hess's law. We're trying to get all of these equations to add up to the formation equation. Lithium starts out in its solid state, that's its natural state, and we can turn that into a gas. Now, that requires energy to separate those things. And that's right here, the energy of sublimation. That's positive 161. So the energy of sublimation is positive 161. All right, so lithium is now in a gaseous state. And now I need to take the lithium, gas, and I need to give it a charge. Okay. Well, that's ionization. So my ionization energy, I can look up in that chart, is plus 520 kilojoules. Okay. So lithium is now taken care of. We went from the solid state to the gaseous state, and we gave it a charge. Bromine's a little bit harder. Okay, because it starts out as Br2. So the first thing we need to do is break that bond. There's two bromines, and they're in the liquid state. Well, let's turn it into a gas first. Bromine gas. Okay, that's vaporization. So that's my energy of vaporization. You can just see how here we've had a lot of different enthalpies. They're just descriptions. That takes 30 kilojoules. Enthalpy of vaporization of bromine. And then we need to break it apart because we need it to be atomic instead of a molecule. So Br2, and we'll call that a gas, turns into 2 Brs. Now this is a new one we're going to talk more about later. This is the bond energy to break that. It's going to take positive 193 kilojoules. Now here's where we get, let me just say bond energy. Okay, here's where we get a little discrepancy here. The molecule we're after is LIBr. You'll notice there's only one bromine there. This particular equation gives us 2. So this is the energy associated with getting 2 bromines. Now we don't need 2, we only need 1. So we're going to need to kind of do some Hess's law action here. We only want half of this. And that means we only want half of this as well. Okay? Half of the bond energy. That means that 193 is really going to give us 96.5, kilojoules. That's all we need for the bond energy. So we need to watch out there because our molecule only requires one of those. And then I need to take one of those bromines that is a gas, and it is by itself, and I need to add an electron to it. Okay, now adding electrons is going to give me my bromine ion. That's a gas. So that's my electron affinity. That's negative 324 kilojoules. So we're just keeping track of all of these energies. We will add them together here in a little bit. And now we have lithium as a gas ion. We have bromine as a gas ion. The last thing to do is to put them together. And this is our most favorable term. It's the biggest one on this chart, the lattice energy. Two things come together. It's exothermic by the greatest value, negative 787. So now I can actually take my ions, lithium, gas, ion, plus a single bromine ion that is a gas, and that will make LiBr solid. And that term is negative 787. Okay. So this gives us everything we need. We have all of our energies here are going to add up. This equation is going to give me my formation equation, and the formation equation is what we did above. Li, we started with lithium solid. We started with bromine liquid, and we got LiBr solid. And the heat of formation of this equation is now going to be all of these terms added up. So I've got 161, 520, 30, half of the 193, which is the positive 96.5, and then I've got two exothermic terms, electron affinities, negative 324, and then the lattice energy is negative 787. And we see that despite all of those steps, our formation equation, that lattice energy is really drives it, makes everything favorable is exothermic, is negative 304 kilojoules. Okay, so we just add all these guys up, kind of like we did with Hess's law, to get that one. Now, to solve these, you really need to be careful. This one was LiBr, and we needed one bromine and one lithium. So the one bromine comes diatomic. We needed half of that bond energy. What if we needed CaBr2? Well, this one has a little bit different criteria. Here we need the total bond energy to get both bromines. But for this one, we would need 2 electron affinities to get both bromines to be ionic. And here for the calcium, we would need an ionization energy for the first positive one charge, and we would need an ionization energy for the second charge. So we need to be very careful to look at the ion that we have. What is the molecule at hand? How are we going to manipulate these terms? Sometimes we need two of things. Sometimes we need total bond energies, sometimes half bond energies, and how do they come together to make the molecule? Here's what that looks like in graphical form. It's just the overall energy changes. It's good to note here that here's our delta H, final minus initial. That's our formation. But we start with our solids and our gases, our formation equation with elements in their natural state. And then a lot of these terms take energy. It takes energy to make a gas. It takes energy to take off electrons. It takes energy to break bonds. But then our electron affinity is very favorable, and our lattice energy is very favorable. So we can just kind of map the energy changes as we go until we get to our final product. All right. So for each set of ionic substances, select the one with the higher lattice energy. And this is just the one that comes together, not the formation, the lattice energy, and explain why. Well, it's ionic again. Okay, so we have Q1, Q2 over R, because charge and distance is how we have positive and negative ions. This is what describes the attraction between them. So this is very similar to their bond to strength energies. We're just calling it lattice energy now. CSF and LIF. They're both +1, -1, so we can't look at that. So the smaller one, LIF, is going to have a higher attraction, more exothermic lattice energy. Same thing with NABR and NAI. They're both +1, -1. Bromine is smaller than iodine. That will be a stronger ionic bond, higher lattice energy. Now here, the sizes of sodium and calcium are different, but if we put this +1, -1 over the radius and +2, -1 over the radius, we kind of have to make a judgment call here, and it's this +2, -1 is going to be a stronger charge because that allows me to double the numerator, to make it 2 times bigger, just having that +2 charge. The radius of sodium is not going to cut it down significantly to overcome that. Radii don't change very much between the bonds as much as the charges do. So the charges, with these two variables, the charges are going to be more important. If I had +2, -2, and I multiply those together, that's a factor of 4. That's going to be a lot stronger than +1, -1. Even just having that +2 doubles the attraction up here in the numerator. So charges are more important than the radius. Li2O and Na2S, they're both +1, -2, so we're going to look at the smaller one for Li2O. And that'll wrap up the ionic bonding and the lattices.